we've seen that if we choose bases for a vector space V and W, B for V and D for W, then the representation map from the vector space of linear maps from V to W to the vector space of m by n matrices is an isomorphism. And that gives us some nice information about this vector space of linear maps from V to W. So if here we're assuming that little m is the dimension of W and little n is the dimension of V here. So for one thing, it tells us the dimension of this space of linear maps, which would be a bit hard to know what this dimension is just thinking about linear maps from V to W, because I mean, who knows how many linear maps there are? It's hard to say. But since we now know that this space of linear maps is isomorphic to this space of matrices, well, we know the dimension of the space of matrices. It's just the product of its number of rows and number of columns, and that's little m times little n. So that means that the dimension of this space of linear maps is also little m times little n. Another thing that this gives us, this isomorphism, is a nice basis for the space of linear maps. We have a nice basis for the matrix space, right? That's just all of the matrices that have a 1 in a single position and then zeros elsewhere, right? So just for example, for M22, our basis looked like this, right? Just 4 matrices, each of which have a 1 in a single position. And of course, there's a similar basis for any other matrix space of any size. But since this representation map is an isomorphism, if we take each one of these basis elements for mn and do the inverse of the representation, we will get a basis for the space of linear maps. And here's actually what you get if you do that. So if you have your basis B is beta 1 through beta n, and your basis D is gamma 1 through gamma n, then the basis of linear maps that you get is this basis here. So I'm calling it epsilon ij, and to tell you what epsilon ij is, I have to tell you what values it takes. Remember, epsilon ij is a linear map, right? I'm telling you a basis for this vector space of linear maps. So each basis element is a linear map. So to tell you what linear map, I have to tell you what it does to the basis for V. And epsilon ij, it takes the kth basis element, and if k is equal to j, right, so if this one is equal to that one, then it gives you the ith basis element for the codomain space. And if k is not equal to j, it just gives you 0. Right, so what epsilon does is it just right, it's basically watching for the jth beta. If it sees the jth beta, it turns it into the ith gamma. And any other beta, it just sends to 0. Okay, so why is it that this is the map that this basis of linear maps corresponds to the basis of the matrix space that I was describing? Well, let's just find the representation matrix for this linear map. So how do you find a representation matrix? Remember, you start in V. So here we have epsilon ij up here. V is isomorphic via rep B to Rn. W is isomorphic to Rm via rep D. And then in the bottom here, this is the matrix that we're trying to find. So this is, I guess I should write it out, it's rep BD of epsilon ij. Okay, how do we find the representation matrix for epsilon ij? We take a basis element from our basis B for V. We hit it with this, we hit it with the linear transformation, And there are, right, the two cases are if j is equal to k, we get gamma I, and otherwise we get 0 if j is not equal to k. And now we hit this with rep d. Okay, so what does rep d, so there are going to be two cases. There's going to be one case when j is equal to k, and the other case is when j is not equal to k. Of course, when j is not equal to k, you just get 0. This is the 0 vector, by the way. All right, and what happens when j is equal to k? So what does rep d do with gamma I? Well, right, remember what rep d does is it writes this vector in terms of the basis d, which is the gammas, and it pulls off the coefficients. Well, the only non-zero coefficient, since gamma I is a basis element, the only non-zero coefficient is the ith, and that coefficient is a 1. So what we get here is a vector that is a vector that's all zeros except for one spot that has a 1 in it. And where is that 1? It's in the position corresponding to this basis element, but that's the ith position. Okay, so so what do we get when we put all of these together into a matrix to get the representation matrix? So rep BD of epsilon ij is, what is it? So every column except for the kth column is just nothing but zeros. So zeros everywhere except in the kth column. And sorry, I guess I should be saying j, not k. So except in the jth column. And what happens in the jth column? Well, in the jth column, the jth column is this vector. So zeros everywhere except in a single position. And that single position, where there's a 1 there, is in the ith row. So just like I said, the representation matrix for Eij is the matrix that is 0 everywhere except in the ith row and jth column. And of course, as I and j vary over all possible combinations of rows and columns, these matrices form a basis. So you can see now that the epsilon ij's correspond to our usual basis for the space of matrices, M sub Mn. Of course, what these maps actually are depend on the basis, right? The definition of these epsilon maps up here depend on the basis, right? Because the basis here, the basis for W shows up there. So different choices of bases for V and W will give you different bases for the space of linear maps from V to W. But that should come as no surprise because choosing different bases was how we sort of cooked up this representation map to begin with. So of course everything depends on the basis.